Welcome to the Here's a Summer of Programming Languages. Have you ever asked yourself, am I using a suitable programming language for this task? Then this collection of introductions to programming languages used in research software engineering has something for you.
Welcome, my name is Timo Betcke, and today I'd like to talk a little bit about Rust, why we're using Rust in our group, where we've been coming from, and what our experience is with actually using Rust. So first, a little bit of background. So I'm a professor of computational mathematics at University College London. And for years, we've been developing a software package called BEMPP, or its later version BEMPPCL, which solves electrostatic, acoustic, and electromagnetic problems through boundary integral equations. So it started originally in 2011, first as a C++ project with a very shallow Python API. But over the years, we moved more and more features to Python. And in 2018, we completely redesigned. So as a pure Python library with just-in-time compilation through OpenCL kernels, actually CPU OpenCL drivers mostly, in order to implement low-level computation routines which do not work well in Python natively. But now a few years ago, we started facing the challenge of how do we actually move up to clusters? How do we implement complex algorithms like the fast multiple methods and all these kind of things within a pure Python environment? So, and obviously limits of Python were just-in-time acceleration. So Numba is a very good library for this. OpenCL is available. These are good for certain high throughput workloads, for example, array handling, similar problems. But complex algorithms with many Python callbacks were very, very difficult to optimize. And we ended up with the problem, we moved more and more over to Numba and OpenCL. But the more we moved over, the more our code actually looked like low-level code, and the more we were actually suffering from this problem of having, from time to time, the Python interpreter in the background and lots of low-level code that we were just in time compiling and just did not work well anymore. And we actually have a paper in which we are describing our experience with doing this. So we considered a bunch of different options for the future. We knew we would have to go for our cluster developments to go to a more low-level language again. So obviously, we could have gone back to C++. We have lots of experience with C++, but C++ has the usual problems, the CMake, deployment difficulties, complex projects. That's something that in the past took a lot of time from us. The skilling up for new PhD students to actually work on code. And it's not just getting them on the level that they can actually modify to C++. C++ has a problem on very easily runs into undefined behavior, and actually learning the skills to use design principles that avoid this problem. That's very, very difficult. It takes a lot of time and often more bandwidth than is available for a PhD project. And also, there was very little research novelty for doing things like FMM and other algorithms, C++. Other groups are doing this, so why should we do the same again? Obviously, we've been looking at Julia, and Julia loves to promise close to optimal performance, and it can actually achieve this as well. However, optimization can actually be difficult. So Julia loves to hide what it's actually doing because it promises to be a simple language, much simpler than C, C++, other low-level languages. But if you want to optimize really, really well, then again, also in Julia, we have to look at the low-level stuff. What's actually the generated output? How do we optimize types and so on? There's by now, there's a good knowledge available for this. But still, the faster you want to be, the more low-level also Julia is becoming. And the other problem for us a very practical one. We cannot easily use Julia as a backend to Python frontend. And we have lots of external groups using our code and are used to the Python frontend. So that was also something that was holding us a little bit back from using Julia. So what's our option? Well, I knew about Rust. I had over the time, I had done a couple of MSc project students with Rust, just to play a little bit around with the language, get to know the language. And so we thought, yeah, why not? And actually, why not? So compiles down to bare bones code. So there's no runtime system or garbage collector required. It's got very modern package management and deployment. So configuration files, even for complex projects, are very short. Dependencies are handled automatically. You just list the dependency. If it's not there already, it's just downloaded by the package manager. It's like very similar to Node, to Node.js and its package management. Then there's a borrow and lifetime checker, which you're going to come to, which prevents most memory errors from other languages. And when we were still doing C++, we were fighting these issues a lot of dangling pointers and why references suddenly disappeared, especially in complex multi-threaded algorithms, or also why certain variables were not cleaned up when using shared pointers and so on. So that took a lot of effort. Rust essentially does away with this because the compiler handles everything. So we'll discuss this in much more detail later on in the talk. Then integration into the Python ecosystem is very simple because Rust actually talks really, really nice C, and Python interfaces with C. So it's very easy to integrate Rust projects into Python. There's a growing scientific ecosystem. It's still a little bit Wild West, but it's growing. It's becoming more prominent. And obviously, there was a lot of scientific curiosity to do something new and to do something fun. So let's just get started. And in this talk today, we're going to talk a little bit about Rust, but then I'm going to show you lots of practical code snippets on the slides so that you actually see how it looks like, what it means to develop code with Rust. But first of all, just actually how do you get started at all? Actually, that's very simple. Obviously, a lot of Linux package managers and so on, they come with Rust compilers. But I would always recommend to simply install rustup from rustup.rs. It's a very simple website, just one line to copy over to your computer. And this downloads a little script, the rustup script, which installs the Rust compiler environment into your home directory. And with this, you can always keep your installation up to date and always fresh. And in our experience, it's the most trouble-free way of doing this. A lot better usually than using the compilers that are coming from the package manager, where you never know when they will be updated. So, and then to start a new project, that's actually very simple. Just say cargo new demo. So cargo is a general Rust building, deployment, documentation, and everything tool. Cargo is essentially a framework that's extensible through plugins, and they're plugins for any kind of situation. And so we actually use Cargo even to start MPI jobs because there's a very nice MPI plugin for Cargo. So anyway, you say Cargo new demo, for example, and then creates an empty application for you. And then you can just say Cargo run to run it. Obviously, the created binary, you could also start without Cargo, but it's a little bit deeper in a build directory, and Cargo just starts this binary so that you don't have to manually go to these build directories. And then out comes hello world. So what does it look like? Essentially, there are two files being created. So there's a file cargo.toml being created, which just says, has a section package, name equals demo, version, then the Rust edition. So Rust, in order to develop the language, it knows about editions. And every couple of years, a new edition comes with new language features. And then by specifying an edition, you can tell the compilers what kind of language features are actually allowed and which are not allowed. And then below you can just list your dependencies. In a simple Hello World program, there are no dependencies necessary. If you had a more complex program, you would just list the Rust packages that you needed. It would automatically look them up on crates.rs, which is the central package repository, and download them. But you can also directly specify GitHub repositories, or you can specify local paths, development dependencies, anything you like. It's very simple to add in dependencies. And then Cargo handles the rest of the package management. And then main file looks very easy. It's just a simple function, fn main, print line, hello world. That's it. So let's come a little bit to the language features of Rust. And one of the core features of the Rust is the borrow checker. And if you like to read Reddit forums or Stack Overflow from time to time and have looked up a little bit of information about Rust, one thing you will come over again and again is the term of fighting the borrow checker. So why do Rust users always fight the borrow checker? So first of all, experienced Rust users never fight the borrow checker. But let's talk about what it is. So references in Rust are called borrows. So if I do a reference, this means I borrow the type. And but Rust is very strict about borrowing, about references. So data cannot be modified after a borrow has been created. And it goes so far that I can have an arbitrary amount of non-mutable borrows. So I can create an arbitrary amount of references to my data which are non-mutable. Or, and that's an exclusive or, I can create exactly one mutable borrow. Okay? So how does this look like? So I have in the upper right, I have my variable x, which I assign the value 5.0. It's an f64 float 64 value. And then I can say let y equals reference to x, and that's now a reference to an f64. And I can also say let z equals reference to x, it's reference in f64. I can print out both and it's fine. Okay, so I've created the variable x and I've created two borrows to it. It's all good. So let's now look at the example below. So I said here, let mute x equals 5.0. Okay, but now the difference is mute. Mute stands for mutable, so I'm now allowed to mutate the variable. But now I'm creating with y, I'm creating a reference to x. Okay, but now I'm assigning x equals 2.0. And now Rust is complaining and it refuses to compile. Namely, in the next line, we want to use y again, but we are not allowed to use y anymore because we have modified the data. So we have created here a borrow, a non-mutable borrow to something, to mutable data. So meaning we're not allowed to mutate this anymore. So, or we are not allowed to have the borrow. Then, okay. And here I cannot assign to x because it is assignment to borrowed x occurs here. If we were to delete the print line statement, then it would work because it would just say, okay, we've created y equals reference to x before. The compiler sees it's not needed anymore, it's not used anymore, so it's okay, we can just keep on changing with x and so on, and the variable y itself, the reference y, is dropped before we modify the variable. But because we use y again, we cannot modify. This becomes an invalid statement here. Okay, and this is one of the core features of Rust, that we can always only have one place where we are actually mutating a variable. I've created x as being able to be mutable. So x owns the 5.0 is mutable. I cannot create other references to it now while I'm mutating the variable. That's very important here. So there's lots and lots of more stuff to the borrow checker. And a Rust expert would now say, maybe it was a slightly imprecise description that I've been given, but that's the gist of it. When we have data, there's only one place, one owner of the data who is actually allowed to modify the data, and otherwise we are only allowed to have non-mutable borrows to the data. Okay, but if we want to still being able to modify the data, these borrows don't. We cannot have these other borrows that are alive at the same time. So I've been talking a little bit about being alive and the borrow checker, what it means to be alive. there's a notion behind this, which is called lifetimes. And lifetimes in Rust are a concept that are very explicit. And most programming languages deal with lifetimes. Compilers deal with lifetimes all the time. But most programming languages do not have a way to explicitly work with lifetimes. Rust is different in that respect. So Rust has built in, as part of the language, as part of the syntax, a way to actually work with lifetimes and to hit the compiler with lifetimes. So how does this work? So Rust has an explicit notion of lifetimes. Lifetime checking happens at compile time. And in a lot of cases, the compiler, like in other programming languages, can figure out what the lifetime is of a variable, but not always. And when we cannot do this, then we need to put an explicit lifetime signature. And a very simple example is this function here, this fn function, what's my lifetime? And it's got two funny annotations. It's got these two annotations, prime a, prime b. These are generic lifetime parameters, okay? These are essentially lifetime parameters. They are also generic variables, but generic variables who are standing for lifetimes, okay? So, and then we have S1 is a reference with lifetime A to a string, and S2 is a reference with a lifetime B to a string, and we are returning a reference with lifetime A to a string. And what we are returning is this function is simply S1, the first string that we put in. Now imagine we would not have lifetimes here, okay, like in C++. We would simply hand over the a reference to S1 and a reference to S2, and back comes a reference to a string, okay? C++ would allow us to do this, but C++ wouldn't know actually which reference are we giving back, and we could quite easily, in such situations, we can run into this issue of dangling references, that we're returning a reference to something that's then later not alive anymore. With lifetimes, we're explicitly denoting what's actually the lifetime of what we return. Namely, we have input, we've got lifetime A and lifetime B, and we're returning something with lifetime A. Okay. And let's look at the two bottom picture, what it means in practice. So we've got here a variable S1, which gets the string hello. And then we've got a variable out, which is also a reference to string. And then within the brackets, okay, within this code block, we're creating a small code block. We're defining in this code block S2, which is just world. And we are saying out equals what's my lifetime S1, S2, okay, within this closed code block. Now the variable out is defined in the outer block, so it keeps on living beyond this bracket over here. And then we say print line out, and everything is fine because out is a reference. It's a reference to S1. S1 is defined at the beginning. By the time of the print line, it's still alive and everything is good. Now let's look at the second code snippet. We do everything exactly the same, apart from when we say out equals what's my lifetime, we say S2 and then S1. So we are assigning here to the first variable, we are assigning S2, okay? And now we are going out and we want to print out. Now we cannot do this because S2 here, it just lives inside this block over here. It stops existing here. The variable is dropped here, the end of this block. So if we want to print out here, that's a dangling reference. We are not allowed to use out here anymore. And in Rust, the compiler detects this because the compiler is checking the lifetime. It knows from what's my lifetime, which lifetime is coming back. And the lifetime is coming back is the lifetime of the first variable, which is S2. The lifetime of S2 drops at the end of this block here, so out is not valid anymore. We are not allowed to use it, even though it's defined here as a reference in the outside block. Okay, the compiler detects these issues. That's not possible with other languages. Sometimes, if you have C++, sometimes the compiler can detect very obvious lifetime issues, but not all of them, and we all know these dangling references. Now, the concepts of borrows and lifetimes are closely related, and they're core to the language. And very often we come into this issue that I mentioned of fighting the borrow checker. This is very similar to fighting lifetimes. It's very closely connected, fighting the borrow checker and fighting the lifetimes. People, especially beginners, often complain with Rust. They do something with the language that in other languages would be allowed and is fine and it works, but the compiler doesn't want to compile, and then they're trying to design things around and changing things, and then you get the common Stack Overflow, hey, I've been fighting the borrow checker, my lifetimes are not working. That is in 99.9% of all cases, and I've never had a case where it wasn't a case at the end, that this is a good sign that your program design is actually not very good, that you should redesign it. You should redesign your program flow. And I'm saying this out of personal experience. When I started with Rust, I actually treated Rust very much like, hey, C++ with a different syntax with a little bit more safety guarantees. And then I ran into a brick wall because of this borrow checker and lifetime issues. And Rust is a very, very different language. In Rust, you need to be aware of actually who owns data, when is it defined, how long is it alive. So you need to develop much more of a notion of what can you actually do at each given point of time with the data you have, and who's actually allowed to modify data at any given point of time, and who's allowed to access data. If you're not doing this, then the compiler will do it for you, and the compiler will refuse to compile. Okay? So we are going to come back to this topic a little bit. We're going to see in when we have some more practical slides, more examples of this. But this is a very fundamental notions of this. It's borrow checking in its lifetimes. Okay, that's very much core of Rust. There are lots of other goodies. There is, for example, enum parameters can contain data. For example, we often have in our course, we have something called a kernel type, Laplace Helmholtz or modified Helmholtz. And then for Helmholtz, we actually store inside the enum a complex wave number. Or modified Helmholtz, we store a real wave number. Okay? So that's possible. Enum parameters can have associated data, which is super, super practical. One of the applications is actually that the option enum, which is used in Rust instead of the null pointer. So the option enum has two values, none and sum of t. And here you actually see an example of a generic. If you see in C++, then you know this kind of notation of generics. Generics in Rust, they work differently in subtle ways. So don't think it's just templates. It's actually very different from templates, but for the purpose here it's similar enough. So we have an option of some type t, and this option can have the value none, for example, a null pointer, or it can have sum of t. Okay, and then we can actually check for this in the code at runtime, whether we have the none value or the sum value, and they're really, really nice language features to work with this and check this. Correspondingly, Rust does error handling via enums. So Rust doesn't have an exception mechanism. Errors are propagated through return types. And for this, there's a result enum, which has two generics, the value t and an error parameter e. And then either we have OK of t or error of e. And then there's some very, very nice language constructs to actually deal with error types. Now, other very nice thing about Rust is Markdown document generation. You can just write your code documentation within your code document using Markdown. And then Cargo has a document generator, doc, which is going to generate beautiful HTML documentation out of your code. So it's all there. You don't need to download Doxygen or other stuff to do it externally. It's all part of Cargo. Then other very strong features that we're not going to talk about here anymore, because that would lead us very much down the rabbit hole, is actually macros in Rust. So in C++, macros are simply string substitution, and in Rust, macros are powerful language constructs. So we have, first of all, we have declarative macros, which are a safe equivalent of standard C++ macros. They work a little bit similar to C++ macros, but they're not simply string substitution. They actually have semantical information, and they're built inside the language with semantics. Okay, so they are much more than just strings. And then you have procedural macros, and procedural macros are powerful beasts because they allow you to modify program code during compilation. And sometimes you see in Rust code annotation, I'm not going to show is here, but these code annotations, these little hashes in front of function name, and sometimes derive this or use this. These are actually procedural macros which add functionality to function by rewriting the program code during compilation. You can really work with the absolute syntax of the language and rewrite it at will with procedural macros. And that can lead you quite deep down the rabbit hole and lets you do some really, really cool stuff. So, unsafe Rust. Whenever we talk Rust, we also have to talk unsafe Rust. There's this notion always that unsafe Rust is something that is to avoid. No, it's not to avoid. First of all, what is unsafe Rust? Unsafe Rust doesn't mean, oh, that's Rust that is dangerous and it's critical and it's bad. No, unsafe Rust simply means we are in a situation where the compiler, with its borrow checker, lifetime analysis, cannot go far enough and decide in a suitable way what should be done. You need to help it. And essentially, by using the unsafe keyword, you are taking responsibility yourself, and a few things are suddenly allowed to be done, which in safe Rust are not allowed to be done. The key features of unsafe Rust are you're allowed to dereference pointers. So within an unsafe statement, you're allowed to dereference a pointer. Or you're allowed to call other unsafe functions. Particularly, you're allowed to call functions which are, for example, coming from C through the foreign function interface, which are by default unsafe. Okay, so these are the kind of core features: dereference pointers or call other unsafe functions. That's the key uses of unsafe Rust. Okay, and here's a little bit of an example. Imagine we have an array with 4 elements. And we like to have split this up into one slice which specifies the first half of the array and another slice which specifies the second half of the array. Now we can simply do this, there's no problem. But then we actually want both slices to be mutable. In principle, this should be fine because they're not overlapping, they're looking at different data, so no risk. But in Rust, we are not allowed to have 2 mutable borrows to the same data. But here, actually, we do have then 2 mutable borrows to the same data, namely one mutable borrow to the first half of the array, the other one to the second half of the array. And the compiler obviously cannot know that on its own, that this is a safe way to do so. So it cannot go that deep with the checking. So in order to make such constructs possible, one uses unsafe. And so the way this is to be done, we create 2 pointers, one to the first element, another one to the third element of the array. And then with an unsafe block, we are dereferencing the pointers into 2 slices, into 2 mutable slices, and suddenly out we have 2 mutable slices. And unsafe here just means we take responsibility ourselves that we create 2 mutable slices that actually do show 2 distinct memory regions that do not overlap. Okay. Now this is a very simple example. Obviously, the Rust standard library, it does have lots and lots of constructs for this kind of situation. So if you're just working with slices and arrays and need to split them at some point in similar operations, Rust actually already has built-in functions in order to do this, which internally actually implemented with this unsafe pointer dereferencing. So this is fine. Now, we talked a lot about the borrow checker, lifetimes, unsafe, and so on. All this kind of nasty business. now some really, really good business about Rust, namely traits and generic. So Rust has a very modern traits system that is in some sense similar to concepts in C++20, but while concepts is an optional add-on to C++ that was introduced with the C++20 standard, so you can describe functionality by concept, but you don't have to. And if a template randomly satisfies the constraint of the concept, then it's acceptable. In Rust, it's the other way around. Traits in Rust, they're core to the language. And everything you see within Rust and standard library and the core language is actually built around traits. Traits are the core features of the language, and generics don't mean anything without actually traits describing the functionality. Okay, and in Rust, whenever you want to assign functionality to a trait, to a generic, assume that it's able to do something, you have to specify explicitly what traits it satisfies, or the compiler won't compile for you. It's not like C++. In C++, the compiler substitutes the data types or templates and then checks during compilation, does the data type actually satisfy, does it make sense within the context? If I call some method on the data type, does it actually exist? Rust is the other way around. We actually have to explicitly declare what functionality do we expect to have, and that's done through traits. Okay. Here is, for example, a very simple trait. We are actually going to come to traits like this in much more detail. So pub trait unsafe random access by value, that's the kind of trait we use in our own linear algebra library that we're developing. And this has an unsafe function, get value unchecked, get one t unchecked. So that's just an example of a trait. And just to see here that a trait, it actually has an associated type here, type item scalar, and we are returning here safe colon item. So within traits, we can actually specify associated types, which is really, really useful. So let's see. So let's put this all together. And the next part of the talk is about designing a basic matrix data structure. Okay. So, and I've chosen this example because it's quite useful to actually show how it works in Rust to implement structs and traits, how to deal with iterators, where lifetimes actually come into play. Because a lot of code, they actually don't come into play. The compiler is pretty good at figuring out lifetime on its own. Don't always have to use them explicitly. And also simplifying simple units. And I've chosen matrix data structure for this because we all have a good notion, pretty much good notion about what matrices are and how they work. So it's really nice to visualize code with just some implementing some basic matrix structures. So, but first of all, in Rust, we don't have to do everything on. There are very good linear algebra libraries available. Two very popular ones are ND-array and algebra. We're also developing our own linear algebra library, which hasn't yet been fully released, but it's close to it. So, but for a lot of applications, ND-array and algebra are really, really good projects and offer very high level, powerful matrix data types in ND-array, even n-dimensional array types. Okay, so let's start with basic matrix data structures. So we could declare a matrix in the following way. We say pub struct matrix of T. And T at the moment just some kind of generic. And here you see in the struct definition, we haven't actually assigned any kind of trait. Usually when you're designing a struct, you don't restrict the valid data types already by traits if it's not necessary within the struct definitions. You do this when you implement functionality for the struct. Okay. And by the way, also in Rust, you do only have structs. There's no separation between structs and classes. What C++ has with classes doesn't really exist in Rust. Rust only knows structs and functionality that you assign to structs. Okay. So in the structs, we've got two values. We've got the data, which is rec, okay, which is like the C++ vector. It's a resizable heap-based array type. And then we also have the shape, which is a fixed size, compile time, fixed size array of use size, so which is here of 2 elements. And so use size on any standard system is just a 64-bit unsigned integer. Okay, so, and yeah, matrix defined over generic type T, data vector over T, and shape determined by fixed size. Rust doesn't have constructors, so there's no language level support for constructors in Rust, but the convention is that if we implement a new method for a data type, that serves as kind of the base constructor. So we are now implementing the new method here, which is going to serve as our constructor. So we are saying pub fn new, and then we hand this over a shape, so which is a number of rows and number of columns, and return self. And the self, where we said implement, forget about this for a second, for any t matrix of t, and then the self with the big S here just references back to the data type for which you're implementing. So this returns back a matrix of t. Now, what do clone and default here mean? These are traits. So these are traits which are defined in the Rust standard library. And the clone trait is a trait to denote data types that are clonable. Okay? And the default trait denote data types that do have a default value. And why do we need this? Because we're using here this vec mark over here, this vec exclamation mark, and this exclamation mark means that this vec is actually a macro. It's a macro provided by Rust, which makes it easy for us to initialize new array. And this macro, it takes first value, namely the value that's supposed to fill up the array. And here we're using default, and then via the number of elements, rows times columns. Okay, and this default, this may look a little bit strange now. Essentially, default, this is a method defined by the trait default. It just returns the default value of a data type. But how does Rust know which data type should be returned? Rust is actually really good at figuring out types. So it sees here that in the struct itself, data is of vec of t. So if you call it default, it should call default for the data type t. Okay, and now it's going to look up, does t actually implement the trait default? And well, yeah, it does, because that was a condition, must implement default. And then it looks up the implementation of the default function for this data type and executes that. And then at the end, we are filling up self of data, shape. We are handing over those two values to the struct. In Rust, if the handed over values to a struct are the same names as the fields in the struct, we don't have to specify the field names again. So we don't have to say data :data or shape :shape. It's just done like this. Only if these two variables would have different names on the field names, then we would have to use this colon notation, also used from some other languages. Okay. So now we've defined our matrix struct. Now let's get an accessor for this. So we want to be able to access data. And for this, we define this pub trait unsafe random access here. Oh God, we are already in unsafe territory. So we'll come to this, why it's useful to do it like this. And this trait, it has an associated type element, which denotes the actual element type, scalar type of the matrix that we're going to use then. And then we have a function unsafe fn get unchecked applied to self. And then, so the self is then whatever we implement the trait for. And then we hand over a row number and a column number, the row and the column. And it returns back a reference to the corresponding element. So why are we doing this as unsafe? Well, safety. Row and col must not be out of bounds. We're actually not doing any kind of bounds checking here. So you could, in a 3x4 matrix, you could here say 1000 by 1000, and it's done without bounds checking. Why do we define such a trait without bounds checking? Well, simply for performance. There are certain type of operations in matrix data structures where actually you want to iterate through without constantly doing a bound check. Okay, so we separately define an unsafe trait here that doesn't do bound checking. That's actually also done within the standard accessor traits for vectors in structs and for slices and for similar data structures. They always have an unsafe accessor routine without bound check and a safe accessor routine with bound check. Okay, so that's so far, but that doesn't give us very much here. That's just a trait. Okay, now let's go on. So first of all, we want to define a safe trait for just random access with bound check random access. For this, we have the pub trait random access, also type element here, and this returns the element at the given row and column. You see there's no unsafe here. Okay, just have fn get self row and col, but it returns now an option. Option of a reference to an element. And remember, an option can be either none or it can be some of something. If it's none, this will denote that the row and column that we've given over here is out of bounds, so we return back a none. Or if it's some of something, that is if row and column are inside bounds, and we return some of the reference that we wanted to actually have. But how can we figure out that we are inside the bounds or not? We need some kind of notion of the shape of the array. Okay, so let's define another trait, namely pub trait shape. Okay, which is a trait that returns shape of an array, and it returns a standard shape method, returns a usize colon 2, so number of rows and columns. But we also have a little bit of helper routines here, return the number of elements in the matrix, fn lem of the usize. And you see here something that's called default implementation for a trait. This is code that is specified directly inside the trait because it only uses the current trait. So we have let rows, kites equals self.shape, and then we return rows times kites. So that's just now implemented automatically for any method that implements a trait shape. So you don't have to always rewrite this function. Or fn is empty, we just check self.len equals 0. Okay. So we have a trait shape now, and we have a trait random access. Let's bring them together. And what we can do, we can implement random access for any t where, and here you see the where clauses, and where clauses are very core to the concepts of traits because with them we can list a whole bunch of almost arbitrary constraints if you want to have for what situations traits actually make use should be implemented, where t itself satisfies unsafe random access and shape. So we define random access for any type t which already satisfies unsafe access and shape. And the way it works, we are getting back the number of rows and columns. We check if our row is smaller than rows and col is smaller than cols. And if that's the case, then we return sum of unsafe, because get unchecked is an unsafe routine, so we need the unsafe keyword, and otherwise we return none. Okay. So we've now created a safe array access for two-dimensional array access for our data. Okay. And very interesting, you see here in this whole thing, in this trait definition over here and the trait definitions over here, we have not one mentioned explicitly what is actually the struct we're working with. So we've written code here that only depends on traits that we are specifying. And that's very typical in Rust. If we are abstracting away from the actual struct that is implementing code, we had our matrix struct at the beginning, but any code that implements the unsafe random access and shape would now have automatically implemented random access. It doesn't really matter what the underlying struct actually was. We are building up our code by defining a certain set of basic traits, and then we're building and building and building on top of those traits. And that's very typical in Rust, and a lot of Rust libraries are built like this. Okay. Similarly, you can do traits for mutating elements, so you can do unsafe random access mute and random access mute. Why do I have to do those separately? Because a mutable reference in Rust is very different from a non-mutable reference. These are really different types. So therefore, if you want to have mutable access, so get back a mutable reference here, that's a different return value from a non-mutable reference, so requiring a different function therefore. So in Rust, mutable and non-mutable references, they're strictly different objects. You have to write separate functions for mutable and non-mutable access. This might seem a little bit excessive for you, and you say, okay, I have to write more function in C++, but it actually gives you a lot of more safety in terms of coding, because you much clearer specify where actually is mutable access needed, where is non-mutable access needed, and you're only using the corresponding function. And it's also very important for the borrow check itself, because the mutable function here, it takes a mutable borrow here. And remember, we can only have exactly one mutable access to a data, not multiple ones, okay? And then here we have the trait for mutably accessing an element, this pub trait random access mute. Again, and we can then again implement this in a similar way as we did before with the non-mutable ones. Okay, so I've talked about the traits not just now, but how do we connect the struct and the trait? Here, for example, for the shape trait, so and the unsafe random access trait. So we say just implement for any type t shape for matrix of t, and then just say fn shape. And well, we already stored the shape variable explicitly, so the shape function just returns the shape itself. There's nothing more involved. You could imagine more complicated structures where you actually have to compute the shape as part of a function. That would be in such an implementation block. Or if you want to have unsafe random access, then our shape works in this way, where we're doing here, what I've done here is actually column major order access or four times trial access to the data. So that we're going, the data is assumed to be stored in memory by column. Okay. So, okay. There's lots of other nice stuff we can implement for a matrix type. First of all, we don't always want to write .get or to actually access matrix data. We want to be able to use a nice bracket notation. Well, in the standard ops library from Rust standard library, there's this index trait here, which allows this, and the index trait allows us to define this kind of bracket notation, array-like notation for arbitrary data structures. And our index here itself is a fixed array size for two elements, namely row and colts. That's our index. And for matrix T. Okay, so we are just defining here standard ops index, and that's what you would call in C++ operator overloading. Operator overloading in Rust means I'm defining the traits that allow me access to these operators. Okay, and correspondingly also with index mute. An index mute is also always defined in index mute always in such a way that we're using this unwrap over here. That's very typical in Rust. When we have this index notation, we don't want to have a sum or none back. We want directly the value back. So we are calling self.get corresponding index that returns an option of this, and then we are unwrapping the option. And this unwrap at lifetime, it would actually cause a runtime error if we were to try to unwrap a none value, and it would just go through if it's a sum of something value, it would just return inner value. So this gives us this unwrap is a very simple way to at runtime to just cause an exception if a wrong value is unwrapped. Okay, certain library developers therefore don't like unwrap because they say always the user should handle this unwrap. When we are designing matrices, it's actually very standard that we want to have an exception if we use wrong indices to access our matrix data, because then somewhere else in our program is a bug. Okay. Unit tests. Unit tests are part of the core language features in Rust, and that makes generating unit tests for code very, very nice. We can write unit tests in the same source file as we also do other file. And the way we do this, we're creating a little module called mock test, and then we have this parameter here, config test, okay? And this tells the compiler that below this, this should be executed or compiled when we're actually running unit tests. And then we use super : star. This means use everything in the upper module, which is the other code that we're currently working on. And then I'm defining here two tests, an fn new matrix, and we say let matrix equals matrix. Now we have for t, we are using the concrete type f64 and the new 3,4. And then I'm just checking the shape of the matrix, that this is indeed 3,4. And here, setting and getting an element, let mute matrix. Here we're now saying the matrix should be mutable. And now I'm saying matrix of 1, 2 equals 42.0. That's our now bracket notation here with the standard ops index, or more precisely index mute over here. And then at the end, we're asserting that this value was indeed set to 42.0 by calling matrix 1, 2. And this uses the standard index, not the mutable one, because here we are not mutating, we're just accessing. Okay. Iterators. Iterators are very core to Rust, and actually the iterators in Rust are quite comparable to what you have with iterators in Python in terms of how they look and functionality. So iterators in Rust are a very core and powerful concept with its own data structures. And once you implement proper iterators, there are lots and lots of powerful routines that you can run on iterators, like for each routines or certain summation routines, all kinds of stuff, or it's already defined standard library. Then there are extended library like Iterators that give you very fancy kind of windowed iterators that always take 2 elements together and all kinds of other interesting stuff, or zip iterators that allow you nice Cartesian products of other iterators. Or also you have parallel libraries like Rayon, which allow you to turn iterators into parallel iterators. So there's lots of powerful concepts once you have defined iterators for your type. So it's always good if a type is amenable for iteration over data, then you should tap into this iterator framework for Rust and write adapters for this. And I just want to show how this works here for this matrix type, just to show what an iterator in Rust actually is. So we have this pub struct matrix iterator here. And the matrix iterator now has something that we haven't seen before. It has a lifetime. Okay. Before we haven't worked with lifetimes, now we start having to work with lifetimes. Why does it have a lifetime? Because it stores a reference to a matrix. And the iterator, by default, can only live as long as the matrix is alive, because it stores a reference to a matrix. Okay. In Rust, by default, whenever you have a struct, no matter whether it only stores one reference or multiple references, you always have to specify lifetimes for these references. So here, lifetime suddenly becomes a secondary parameter, and matrix is now a reference with this lifetime a to not. Okay, and then we've got the current position of the iterator and the overall length of the iterator, which is the number of elements in the matrix. So, and how do we implement the iterator? There's an iterator trait in Rust, and once the iterator trait is implemented, you have access to all the nice iterator functionality that Rust offers that built on the iterator trait. And to implement this, all you need to implement is the next method. And the next method returns an option of self. And if yes, the valid, so if self.pos is more than the self.length, as the length of the data, we are just returning the next element. And to do this, I have a 1D access trait, unsafe 1D access, which just returns the matrix data from one-dimensional index, column by column. Okay, and then we advance the position of the iterator by 1 and return sum of item, or if the iterator is already at the end, we just return none. That's the convention in Rust. As long as the iterator is valid, we return sum of something. If it's not valid anymore for you to return null. The beautiful thing about this is the underlying Rust compiler knows iterators well, and all of this checking over here with some or none, so on, and this unwrapping of values, this is all optimized away. So if I implement an iterator in this way and I iterate through the memory position as the matrix is actually within aligned within memory, then if I do operations on this iterator, like for example, I do an element by square root or something, the compiler will just auto-vectorize this with SIMD because it sees that the iterator just iterates through the data in memory order. Okay, all of this stuff here is really, really nicely optimized. This was an easy thing, iterators just for reading access. Now for writing access. I just want to give this example just to show that iterators in Rust can actually be complicated when it comes to lifetimes. So, namely the mutable iterator. For a lot of cases in Rust, when you're just dealing with slices, existing slice data structures, and you don't need to worry about all of this, but if you do implement your own iterator, you need to worry about this. And I'm not showing this here because I say this is a core language feature that you now have to learn. The first time I implemented my first mutable iterator was quite a little while into working with Rust. But I want to show that lifetimes actually can create complexities, and that Rust, with this lifetime notion, is not always an easy language. Namely, we want to implement the iterator for matrix iterator mute. We want to have a mutable iterator. And the type that is returned by the iterator is a mutable reference. Now, that's in some sense is a bit problematic, because if I iterate through my data with next, and I'm returning one mutable reference after the next, in principle, I could store those mutable references and then suddenly have lots and lots of mutable references to different elements of the same array. But we are only ever allowed to have a single mutable reference, not more. But the compiler doesn't know that this is okay here, that when we're calling next, we're actually advancing the memory and everything is fine. So we have to help the compiler here, okay? And this is done within this next method. So we have this if self.post more or less self.length, that's all the same. But then I have this unsafe statement here suddenly, and I'm having this variable, this function here, transmute. What transmute is doing, it's transmuting a reference to mut element to a reference with lifetime A to mut element. Meant by lifetime A was the lifetime of the matrix, okay, of the reference of the matrix. So we are, by default, Rust here with this mutable reference, it gives it only the shortest possible lifetime, namely the lifetime of @mute self, which is only life as long as the function lives. And when we are then returning, getting out, it cannot cast this to something with a potentially longer lifetime, namely the lifetime of the whole matrix. So what we have to tell Rust, that this is actually okay to do. And so we're using the transmute function to transmute the lifetime here. Transmute is a big, big hammer which can do all kinds of nasty stuff. It's kind of a little bit like the different casting variables in C++. It's unsafe, and here we're using transmute to transmute a lifetime. Usually, most of the time, you shouldn't have to use transmute for anything. This is one example where you have to use it. And I wanted to show this example to see that there are complex situations where the compiler just cannot figure out that lifetimes are okay. And then sometimes we really have to have the compiler for this. Okay? Otherwise, this code would not compile. So there are a couple of more things we'd like to do. For example, we'd like to implement matrix addition. Well, for this, we just have the add trait. And so we say implement tclone plus default plus add, come to that other dot shape plus unsafe access, and then we have this trait add of other. And the add trait, this is essentially operator overloading. Okay, and other, that's the right hand side of the add operation. So we are implementing the add trait for matrix of T. That's essentially the left hand side, and the right hand side. So behind the plus, that is the other type, and we have to specify this. and I'm doing this here in the implementation top, our T should be clone and default, and it also, T itself should support adding up numbers. So if I'm adding up two matrices, I must ensure that actually the underlying element type also allows to be added. So that's I'm saying here, T itself must support add. And then the other type here must support a shape, and actually unsafe 1D access with element equals T. Okay, here element equals T, and my T here, and I have a matrix of T, means the other type also has the same element T, because we have the same T in unsafe access from the other type and for our matrix itself. And then the output is again a matrix. And the way we are doing this, we are just iterating through the data. We're using a zip iterator. This is actually from the Iterators library, which allows us to put different iterators together, put together the mutable result iterator, self iterator, and right concise iterator, and we just say star out equals 1 in.clone plus in2.clone. Okay. And if you compile this code, all the craft about iterators, all of this stuff is going to be optimized away, and out comes, if you do the iterator itself in terms of memory order, it will nicely SIMD optimize this. If T is, for example, a standard F64 integer, anything that can work with SIMD. Okay. So now this here is quite interesting, because add itself takes self and RHS, but it doesn't take it without references. It takes the values itself. So it takes ownership of these values. So if I say res equals mod1 plus mod2, that works, but the add function now has taken ownership, doesn't give back ownership, so nobody else can work with these variables mod1 and mod2 anymore. Usually we don't want this. We want to hand over references. I want to hand over reference mod1 and reference mod2. I could have implemented this with references straight away, but then if a user is just lazy and just wants to write mod1 and mod2, that then doesn't work. Okay, so in Rust, references to types and types are fundamentally different. In the add method, we would have to separately implement this for the different types, or there are certain traits available which allow us from types itself to get references back. But we need to deal with this situation here. Okay, that's something to keep in mind. Again, another example that references to types are fundamentally in Rust from types itself. Okay, so I hope I haven't scared you off Rust. So a lot of what I've been talking about sounds a little bit complicated. So why should we actually do this? I mean, Rust, it forces to think you about data and who owns data. It enforces a different coding style than C++, and that's the biggest beginner mistake, that people start Rust and they think C++, because often they come from C++, and they treat Rust like C++, like a kind of more modernized C++. And then they quickly realize, oh, it doesn't really work. The trait system is all suddenly very different, and they have to think differently. And that's actually the point when you actually start learning Rust. Rust is as much about designing your code than it is about the syntax, because the kind of restriction about ownership and lifetimes, you have to think about how you design your code. The result of this, though, is code that is much, much more robust than code you get from standard C++. Okay, so it's a learning curve that's much higher than Python and Julia, and closer to C++ than scripting languages. So Rust is not more difficult than C++. Rust is actually a bit easier than C++, even though it might look a bit difficult. The reason why Rust is easier than C++, you don't have undefined states. In C++, it's very easy to get into undefined behavior. In Rust, undefined behavior is a compiler bug and fixed by the compiler team. Okay, so that makes Rust at the end still a bit easier than C++, but it's not as easy like Python to learn. Okay, you have to learn about concepts like ownership and lifetime and so on, things you might not have thought about beforehand. But once learned, the development speed of Rust is actually, and that's quite interesting, and something we noticed in our group, it's much closer to Python than to C++, because all the usual nasty pitfalls that you run into with C++, and when you suddenly have the segfaults and you're debugging segfaults again and again, they all fall away. The compiler does it all for you. So the only time I ever had seg quotes in Rust, actually I remember a single time, very actively remember a seg quote, was when I was calling a LAPIC routine from Rust, and then in the unsafe block I was allocating the wrong amount of memory buffer for the LAPIC function. Okay, but even then I could find the seg quote very, very easily, but because I knew it had to be in the unsafe block and very quickly. So otherwise I never deal with seg quotes in Rust. Just doesn't exist. So, and the trait system is incredibly powerful type system, but it's very different from C++ templates. Okay? So for example, in C++ templates, what's very typical is template specialization or partial specialization. So that doesn't work in Rust. The way the trait system works in Rust is really not part of the language. So you can do stuff like template specialization in different ways in Rust, but you actually have to think differently because the trait system works very different from C++ templates. And that's something that, especially in the beginning, people would often run to. Why doesn't it allow the trait system? Why doesn't it allow me to do this? Because it doesn't allow it because templates C++ side are a simple substitution mechanism. Rust templates are much, much more. They define a set of rules in which you have to work. And then when you define new traits, you define new rules. They all have to work together. Okay. So, but the advantage is, again, when you make a mistake, that the compiler messages you see, there are 2 or 3 lines of, hey, you've messed up this trait, or this trait doesn't exist, what you want to use here. While in C++, when you develop there, when you do a template error in a heavily templated code, you've got a whole bunch of lots and lots of pages of template messages until finally somewhere the function tipped on a level where things were going wrong. That cannot happen in Rust. So a compiler immediately tells you why you write what's going to go wrong. And Rust has a nice language server called Rust Analyzer, which is compatible with VS Code, with NeoVim, all kinds of editors. And Rust Analyzer just helps you. It compiles as you type, and immediately when you write something that doesn't quite work, it immediately shows you a message why. You wouldn't be able to do this with C++ templates because C++ needs to pull in the whole program and work through the whole template substitution. Much more complicated to use in C++. So yeah, so how does Rust scientific computing ecosystem look like? Well, we've got basic packages like num, which has lots and lots of basic traits for number types, or Cauchy for complex types. We've got parallel computing. We've got Rayon, which is excellent library for fork-join tasking, the parallelism. We've got HiRSE MPI, which I really, really like. It's probably the best MPI wrapper I've seen, much better than C++ MPI wrappers I know. It's really, really nicely done. Linear algebra, ND-array and algebra on RST, and we're developing PetCRS, wrappers for PetC, FairIS, super interesting project, which is building Rust native matrix decomposition without LAPIC, and very, very performant library for this. Obviously, you have various LAPIC blast wrappers, so this all exists. And we've got machine learning, we've got Linva, which is similar to scikit-learn. TensorFlow has Rust idiomatic bindings. We've got PyTorch RS with low-level PyTorch binding, and we've got Burn, which is Rust native deep learning toolkit. So all this stuff is there, and companies are investing much, much more in Rust, and a lot more libraries are being ported to Rust. So yeah, why would I want to use Rust for a new scientific computing project? So yeah, it offers modern language design, many static safety guarantees. Compiler fixes a lot for you. Sometimes you want to curse the compiler, but usually when you want to curse the compiler, it just means the compiler is right and you're wrong. That's at least my personal experience with Rust. And I had to learn that I should trust the compiler. Excellent error handling, native async support. I really haven't talked about async support, but that's async coroutine, asynchronous routines that's natively built into Rust. It's really exciting. C interoperability is perfect. So Rust is really a transitioning language if you want to go from C to a more modern language. Rust is an ideal transitioning language because it perfectly integrates with C. Performance comparable to C, C++. Sometimes it's actually better as a compiler can optimize more because by default, stuff is non-mutable. And also you have the access rules of only one variable is allowed to access at the same time. So that means you cannot run into aliasing issues. C++ aliasing is a big problem. So in Rust, you cannot have this. Compiler prevents this. So the compiler can actually optimize much more, and the LLVM team is working with the Rust team in order to make specific optimizations for the kind of knowledge that the Rust compiler has about the language. Okay. Unparalleled tooling. So Cargo supports unit testing, benchmarking, documentation generation out of the box, and we actually have plugins for LLVM code inspection. It's super cool. So I just Cargo, I use a plugin myself that shows me the generated LLVM code for a function. I can immediately check, oh, was this now SIMD auto-optimized or not? So these are things that are really, really messy to do in C++. I can just do here through Cargo. Even MPI execution, I can handle through Cargo. I have an MPI run plugin for Cargo, which works very nicely. No more Makefile is necessary. If anything of the other stuff hasn't convinced you, Makefile should. So even complex projects with mixed Python and anything in, it's just very, very simple build files because you have this one set of tools for Cargo that sees everything. So it's really, really simple and easy to build up complex projects. And you're not writing long dependency files. Even for complex mixed language projects, dependency files are fairly short. Rust Analyzer Language Server provides excellent development support for VS Code, Vim, NeoVim, and other editors. So this makes it really, really easy to work with Rust in modern toolkit editor environments. And Rust is not going away. I mean, it's a relatively new language, but it's got strong investment from Amazon, Google, Microsoft, and others. And if you're running Windows 11 or you're running an Android device, you're actually having a whole bunch of Rust code already in your system. So, and actually Microsoft, I think it was a chief cloud architect, would have to look this up. They famously called C++ last year a legacy language and Rust the future. So Microsoft and others are very, very heavily invested in Rust as a modern, safe systems programming language. And the reason for them is very simple, because it eliminates essentially almost all the memory bugs that they can do with C++. Every bug costs them a huge amount of money. So investing in Rust once in order to shift tooling systems over to Rust and develop new features or transition existing components of the operating systems to Rust saves them a huge amount of money in the long run because they don't do the bugs they do in C++. Okay. So to Rust or not to Rust? Well, it's an excellent choice for new projects that do not require CUDA or Circle. So I'll come back to this in another line. So it's a very good modernization pathway for legacy C code. And existing C++ code, if you're working existing C++ code, I wouldn't think about transitioning this to Rust because it just doesn't benefit from Rust because interoperability with C++ is patchy. If you have C code, it's fine. If you have brand new code base, 0 existing code lines, it's also perfect to use Rust. Interoperating with C++ is a bit of a pain point. Okay. And also GPU compute. So a lot of Rust libraries use GPU compute, but whenever they do this, they use it through C binding to CUDA or other stuff. There's no good native GPU support there yet. There is a Rust CUDA project, which a couple of years ago started off, then fell asleep a little bit, but now it's taken quite seriously by the compiler team, and there are some strong people behind this who are pushing this now to get Rust to be able to write native CUDA kernels within Rust, not just CUDA, also eventually for other frameworks. But this is still some development time. So right now, if you want to write something that uses heavy CUDA or Circle, Either you do it through C bindings, or Rust might not be the best language for this at the moment. Okay, so that's something, if you can kind of factor out small amount of GPU kernels and just write those in C++, the rest in Rust, and just do those with the C binding, that works fine. But if you have a complex application which really needs to use a lot of circular CUDA features, then might not be the best language, Rust. Training need for research software developers is kind of moderate. Rust is different from C++, but not necessarily much easier. It doesn't have undefined states. That makes it easier, but in terms of syntax and language context, it has other complexities than C++, where it prevents most of the common C++ mistakes. But once you are writing a Rust project, the safety guarantees in Rust make it much, much easier to maintain a Rust project than a C++ project. Imagine a new developer in C++ project coming in, doing some stuff, and it turns out they shouldn't have done it, because suddenly it leads to dangling references, because somewhere else in the code they misunderstood how the code internally works, does threading or handles pointers, and suddenly you have some dangling reference there, and you get your weird segfault bugs. In Rust, this cannot happen. Get a new developer onto some bit of Rust code, the compiler will ensure that the developer doesn't mess up. So just because the compiler takes away all of these problems. So, and all the Rust safety guarantees that we've talked about today, we haven't talked multi-threading, but they all extend to multi-threaded environment, which is really, really exciting. It makes multi-threaded development a lot more amenable than it does in C++. Right. Thank you so much. That was a fairly long introduction. If you want to look more into Rust or learn more, well, just join the community. We've got Rust Scientific Computing Zulip chat, in which we are organizing. Or we are also organizing online workshop on Rust Scientific Computing. Apologies, I just noticed I haven't updated here the dates. Rust 13, 14 July, that was an order message. Just look at scientificcomputing.rs. Once a year we are organizing Rust Scientific Computing workshop, and there you can just look up the up-to-date dates of these workshops. Thank you so much for your time, and it was a pleasure.
Thank you for watching this introduction. Please check out the slides on Zenodo, linked below, and see you next time.